All right, so we had a question on the chapter 1 test about writing inequalities represent. Can you guys move to the back, please? Just you're really close to the mic too. So the biggest thing when we write inequalities to be careful about, and where most people make their mistakes, is whether or not the circle's filled in, because that determines whether that point is a solution or that point is not a solution. So always identify it first and remember it and check at the end of the question, did I do it right? So what I see here is we're graphing a set of values that x or some variable that you choose is going to represent. We often just use x as the generic variable. I see that the values being graphed are lower than a certain value, so I'm going to say x is less than. I see that they're not equal to that value because the circle is not filled in, so this does not have the or equal to bar. That only exists when a circle is filled in. So my values are less than. Well, what number are they less than? This number I can count and see is -1. So there x is less than -1. Now that is one of the simpler ones. Here in 15, I see that my values are greater than a certain number because they're going to the right. I see that my circle is filled in, so it is equal to it. Yeah?
Does it matter if the bar is on top or underneath?
It's supposed to be underneath.
Okay.
I don't know why, because to me, it wouldn't matter whether I say equal to or greater than versus greater than or equal to. But when we say this, we like to say x is greater than or equal to. The or equal to comes like second. And then I identify the number. Well, -1, -2, -3, that looks to be about -3.5. So -3.5. Now, 16 and 17 are where it gets hard. If you have an inequality graphed, which is why these problems are probably going to look a little bit more difficult than the test you have to complete, because you have the easier form of the test, which is intentional so that I can help you guys using the harder form. When your group, like your the shaded section is all together, you will end up with one double inequality. When your shaded sections are separated, you will end up with two separate inequalities. So to make this one, you can think of both inequalities individually and then combine them together, which is what I'm going to do. So we see here my range, I'm again going to call it x. So the first thing I see is x is greater than or equal to -1. So I looked starting right here at my -1. It's shaded, so I know it's equal to. My shading goes to the right, so it's greater than. And my value is -1. Also what I see, if I go to this point, is that x is less than the value of 3, no or equal to, because it's not shaded. So now what I can do is write this together, but to write this together, I have to start with my lower value. So I start with -1. Is -1 less than my range or greater than my range? Well, it's on the bottom end. It's less than the range of values, but it's also equal to. Any questions on how I said that -1 is less than or equal to the range that I have shown there? Yeah, so like what's shaded is what I'm calling the range that is shown there, like the acceptable.
Where there are two pointing different ways.
We're going to cover that in a second. So this is only half of my inequality because I also have to say that x, my range here, has to be less than 3.
Oh, okay.
Because -1 is less than or equal to x and x is less than 3. Now, when you write a double inequality, both of these inequality symbols should be pointing the same direction. So when you write a double inequality, both of these should end up pointing the same direction.
Does it matter which side each one goes on?
Nope, because I could rewrite this and say 3 is greater than x is greater than or equal to -1, but that's kind of hard for your brain to start at the right side and move left. We like to start at the left side and move right. So that's why normally we'll start with the lower value and say less than or equal to, and then my variable, and then still less than or equal to, if that applies, some other value. Now, when they point two separate directions, we see the division between my ranges. That means there has to be two separate inequalities. So like this ends up being my answer. I don't need those two separate. Over here, I cannot combine them. I'm going to have two separate. So start with the range right here. Going to the left, all my values of x are less than, not equal to, because my point is not filled in. What's my value? 0. My ranges here go to the right, so they're greater than. So x is greater than my value of 2. That is my final answer. I cannot combine them. I'm done. And a lot of times here, we will say, especially if there's space to do so,
So the two.
and
It's set. Each one represents X.
so there are certain situations where we talk about like profit margins or different things where we'll say there is so much percent of profit or maybe like value of profit in this range, and then there's a gap between the ranges because maybe there's like a break-even point, and then there's so much in this range. So like there are situations where we will have to split what we're talking about.
So a gap, like if it has a pattern but then jumps at its.
Well, what do you mean by pattern?
I mean like a constant rate of change.
Because we're not discussing like rates of change or
No, I
patterns.
mean it has.
So let's say, I'm trying to think of a situation that could be represented by split inequality. Man, applying it to the realistic situation is hard on the spot. I can't think of a real world situation that we could represent with.
So you just represent it as its X, and you just write the inequality for both of the dots separately.
Yeah, when it's split, I just write each of the inequalities separately, and I just throw an and between them. Or you don't even have to have the and; you can just write both of them.
And in 16, you don't even need the and.
16, you put it together in one inequality because it's one range. So, I mean, I'll show another example just for fun. Let's say I had my number line, and we got a point here. Let's say -7. Circle is shaded. My range is all shaded up to this point. Let's say 18, and my circle's open. So I see it's one continuous section. I will have one double inequality represented. If I want to jump right into writing the double inequality, start with your lower value. -7 is less than or equal to, because my circle is shaded, my range. Because x can be equal to -7, or it's bigger. Because remember, the gator's always eating the bigger value. And if you've seen the video of the gator on the golf course, big gator that needs to eat the big value. So then I look at my range from the other number perspective. Well, the range of values, x, is less than the upper value, 18. Now, if it splits, gets harder. So let's say I have my number line, and I'm still going to use -7, but here, going to shade that way. And I'm still going to use 18. But here I'm going to fill this and shade that way. So now that it's split, I have to have two separate inequalities represent this. So now I can say x is a range that is less than -7 because it's not filled in. It does not have the or equal. And x is greater than or equal to the 18. And that's it.
And then the gap in the middle is just.
That's represented by the fact that there's nothing there. So if I try to combine this into one inequality, here's where it falls apart. Say I turn this around. -7 is greater than x. -7 is bigger than these values, right? These acceptable values. And then I say x is greater than or equal to 18. Well, wait. So x is less than -7 and it's greater than 18. This is impossible. This statement that I've just written contradicts itself. So this cannot happen. That's why I cannot combine them into a double inequality. I have to leave them separate.
So how would you solve because there's the solving one, solving the inequality.
What question does that relate to?
This is This is from K. The K.
I know, but
Yeah.
if I do it here. Do you have any absolute value ones on there? Because the absolute value ones are the most fun. So if I do r plus 3, absolute value of r plus 3 is greater than or equal to 7. So again, this is just an example. So if you're struggling on this, I'd be writing this down with me.
Did you have?
Did I have?
Did you keep number 11? Because
I'll upload the. So when I work in here, like any of this
Show me
stuff
that
or
for a
whatever,
second, I mean, number 11.
was this. I don't remember which
I'm struggling.
it related to.
It was
Because I'm not doing verbatim problems. I'm doing similar
No,
problems.
it was an example of how to deal with.
The factoring out Z, yeah, and that video will be uploaded later, but this is where it is. And I'll upload a PDF. Like this, I'll turn into a PDF and I'll upload that as well. But the big trick is you have to factor out the Z. Because it's in two different terms that are not like terms, you have to factor it out and you divide it from each of them, leaving only what they were connected with, and that's what you have to divide by. Okay, but we can come back to 11 if you need more help.
Actually, no, that's. How do you deal with two variables together?
Well, I'll come back to that, okay? So, Jocelyn, you were asking about this. The interesting thing about the absolute value graphs are what is an absolute value, like what does an absolute value do?
I believe it's the distance the number is away from 0.
But if I ask what it does to a number, what is it, or a value, or an expression, if I put something into an absolute value, what do I get spit out?
The positive of whatever number it is.
Yeah, only the positive solution, because, Brian, you're right, it is the distance away from 0. When we're talking about expressions and things, that's kind of hard to think about. I like to call it the attitude adjuster. It makes everything positive. You cannot leave the absolute value without being positive. So this is the positive solution of r plus z, but r plus z might not be positive. The input might be negative. So to solve this, I have to look at actually two different situations. I look at exactly how it's written. R plus 3 is greater than or equal to 7. And then I look at the potential opposite of that situation. My input might not be positive. It might be negative.
But it's positive anyway since it's in the
It becomes positive.
It becomes positive.
So hang with me for so to start out with, r plus, like the absolute value of r plus 3, if I go to Desmos, I don't know if I have this up still. What's an absolute value graph look like? I don't remember right offhand what an absolute value graph looks like.
Like a V shape?
Mm-hmm. Absolute value graph is always graphing a V. So what this problem is asking us, this, where are we, right here? This absolute value of r plus 3 is greater than or equal to 7. It's asking when is the function r plus absolute value of r plus 3 greater than or equal to 7. Here's a really easy way to do this in Desmos. Except you gotta understand how to do it algebraically also. Make another function at 7. So y equals 7 is now my function. This is not plus. And this is a y equals. They already know that though, they made that assumption. So I can look on my graph. For what values of x will this line, absolute value of r plus 3, which I made x, but that's because we're graphing it. So I see I hit that line, that 7 line, at negative 10, and anything less than negative 10 will work. I also hit that line at positive 4, and anything greater than positive 4 will work. But how do we get there algebraically is the question. So how we get there algebraically is looking at the graph that goes to the right and the graph that goes to the left, because that V in the graph, r plus 3, is this right side of the graph. This is r plus 3. Then the other side of the graph, no, not what I wanted. The opposite situation, the potential negative, when I distribute that in, this becomes negative r minus 3. This left side of the graph, work with me, smartboard. You'll get there eventually. The left side of the graph, think about if I continued this line down. That y-intercept would be negative 3. The slope of this line is negative 1. This other side of the graph is representing the graph negative r minus 3. We really have two graphs happening here. But we can put them together by saying it's an absolute value. It makes a v. Everything has to be positive. So to solve this algebraically, we write out both situations. Are there questions on why I write the positive and then the opposite or the negative? It's an No, your question?
No, I get it.
Because it could be positive or negative as an input, the output has to be positive, but we look at both situations.
So if you're multiplying a number on the outside by a number on the inside, it's positive because it's the absolute value, and the absolute value.
Well, it depends on what the value on the outside was.
Well, yeah, but I mean, the value on the inside acts as a positive number.
Mhm.
always. Okay.
Yep, the value inside the absolute value, when you work with it, will act as it's positive. So, I solve these. To solve my first equation, I just subtract 3 from both sides. Because the only thing happening to my variable is the addition of 3, and I come up with a solution r is greater than or equal to 4, which we can see right here. There's my point where it hits 7, where it equals 7. That's 4, and anything greater than 4 is also greater than 7. So when r is 4 or bigger, it works. When r is 4 or bigger, it works. I solve my other situation. Well, I have negative r minus 3. To get rid of that minus 3, I have to add 3 to both sides. I now get, negative r is greater than or equal to 10. Here's where a lot of mistakes happen also. What do I need to do to get a positive r?
Well, you have to divide by a negative, but that means you also have to flip the sign.
When working with an inequality, one of the things that people most often forget to do is if I multiply or divide by a negative, which actually here I like to think of, I really can multiply it by -1 to turn it opposite, to make it opposite. When I do that, it flips my inequality symbol. So now this becomes, the solution is the positive r is less than or equal to -10, which I can see in my graph. If I go to check this in Desmos, this point right here is my -10. Anything at -10 or less than -10 is greater than 7, greater than or equal to 7, which is why those are my two solutions of that inequality.
Just to recap something, the full dot on the graph, on
The closed circle,
the closed circle is
or equal to.
Okay.
Yep, has the or equal to. So what I like to think of, if your circle takes more ink, your inequality takes more ink. If your circle takes less ink, if it's only the circle, it's only the inequality symbol. There's no or equal to.
So, what do you, another question, what do you do with a variable if you have two right next to each other in an equation and one of the variables, what do you do about it? And you just
What do you
reference-
mean?
I
Give me an
don't know,
example.
Maybe something like xy equals 30. Well,
And what are you trying to solve for? You want to solve for x?
X, yeah.
Okay, so
Well,
since
actually, I mean,
you want to make it more complicated,
like
let's make it real complicated.
another number with a variable on it. Like
Here, let's say,
x.
let's solve for y.
Oh,
Yeah, I
wait,
know.
no, he's
I know.
Oh, right.
It's worth it to go over again because it's a really weird type of problem. Let's solve for y in the equation. 4y plus 3xy. I'm gonna make this really nasty. Actually, no, I don't even want to put that here. Let's go 4y plus 2z equals 3xy plus 50. How about that? That's nice and messy. So if you're struggling on that number 11, I would write this down with me and write the solution process. First thing we do. What'd you say? Oh, so tons of scrap paper and resources right here. I have graph paper, and then I have just blank computer paper, because every time I make a copy, they send me one of these on top of the set of copies. So these are all just pointless pieces of paper that it kills me to throw away. So if you need paper, it's all up here. So my first step is get the focus variables together. And my focus variables are what I'm being asked about. That's my variable y. And together, we really mean same side. So to do that, if my y is what I'm focusing on, I either need to move my 4y to the right or my 3xy to the left, and we like to put the variable we're talking about on the left side. It's just easier, it just makes more sense in our brain. So to get rid of this 3xy from the right side, or to move it, quote unquote, to move an entire term and wipe it out to 0, we always use arithmetic. To get rid of a variable and turn the value into 1, we always use multiplication division. So here, we use arithmetic, which is add, subtract. If we subtract away itself, it turns to 0. It completely disappears. So if I do that on this side also, there's no like term to combine with, so it ends up just, being another part of it. So 4y plus 2z minus 3xy equals, the only thing left over there is 50. Now my y's are together, but I also have a term that doesn't involve a y, so we got to get rid of that. So my second step, I'm not going to write out, but my second step would really be get rid of other variables that we don't want. We don't need to solve for z. It's just going to be part of what my solution is, so get rid of it. Subtract your 2z from both sides. When we do that, it wipes itself out on the left side. So 4y minus 3xy equals 50 minus 2z. Any questions on anything I've done up to this point? No. Now is the tricky part. Now what we want to do is isolate the y. And what does isolate mean? Yeah, to get apart from all other pieces. But these are non-like terms. And a lot of times what we would do is like divide by that value, but I can't divide by y over here because that's just going to complicate things. So what we're going to do is a division, but only on one side, which we're not actually performing a division. We're going to rewrite this expression. The expression from the left-hand side, we're going to rewrite with the y factored out of it. So I pull this y out to the front, and I pull this y out to the front. Really, if you want to write out the process of factoring, I divide by y, I divide by y, in order to say y times, well, what would I get when I did the division by y? Here I would get just 4. Here I would still have my minus 3x. The right side, nothing changed. Do you understand what I did there? To do the factoring process, to get the y by itself. Now it's still attached to other variables and other values.
But what if
but
there are no other y's on the side?
If there's no other y's, then you just put just that term by itself, move everything else to the other side, and then deal with getting the y by itself. Add, subtract, whatever you need to do to get rid of that value.
You divide the value.
So say you had like 17y equals, some long thing over here. All you'd have to do to get the y by itself is divide by 17 on both sides.
If you had a variable, how would you do that?
Like a variable attached to it? Like
I don't
xy?
know. Yeah.
Then all you'd have to do to get rid of the x is divide by the x on both sides.
But then there's an x on the other side.
Yeah, but it doesn't matter because all we had to do is isolate the y. So now x is part of my solution, but y would equal whatever it was divided by x. Because it doesn't matter what the right side is, it does what I tell it to do. So in our situation, like in number 11, once we factor the y out, you can really think of any mathematical expression as a variable. Even though there's more involved in here than just a variable, it is its own thing. That expression is a thing, 4 minus 3x. So to move that thing, it's attached with multiplication. So we detach it through division. When I divide a value by itself, it turns into 1. How many y's do I want? Well, I want one of them. So when this turns into 1, that's exactly what I want. But I have to do it to both sides. So now, what throws people off is my solution does not have to be nice and neat and like perfect. It's not a number, it's an expression. So my solution is 50 minus 2z divided by 4 minus 3x. And that is too complicated to do anything else with. We just leave it right there. Then once I start plugging values in, since this is a 3-variable expression, this is in the 3-dimensional plane, the xyz, well not plane, but the xyz space. Once I start plugging values in, then I can do something with this. But right now, I don't know any input values, I'm done.
I feel like I'm missing a lot of the base math for a lot of this.
You might want to go back and review some things then, like solving, like basic solving equations.
We never covered this.
Yeah,
But you should have solved things that would involve like 17y plus 12 equals, you know, like 3x or something where there's two variables involved.
We've done that.
Yeah, so this is just a further manipulation of, do you remember what it takes to solve them? And really, the only thing this added to that process was a third variable that didn't really matter. Because that z, this could have been a number. That could have been 14. Like, the variable doesn't make it any more difficult. It's the fact that you had y in this term and y in this term that is messing with you. Because those two terms being non-like terms made this more challenging.
Okay.
So we can review, like I can go look at what lesson that would be and we can do more review if you want. Let me end this really quick.